Now we are ready to derive the main result of the lecture. As we know, B is an alpha mapping that goes from Rn to Rp. And f is a convex function from Rp to the extended real line. In this theorem, we're going to show that if the domain of the function f intersects the range of the function b significantly, then we actually have the equality in the previous proposition. So what does it mean by the domain of f intersects the range of b significantly? It means the following: the relative interior of the domain of f intersects the range of the function b, that means b of Rn. Okay, so if this intersection is non-empty, then we always have the following subdifferential sum rule. The subdifferential of the composition of f and b at x bar is equal to the transpose of A of the subdifferential of f at y bar. Over here, we use the same setting as the previous proposition. So let me go ahead and write out the theorem and give the detailed proof. Consider the setting of the previous proposition we suppose the following. Suppose that the relative interior of the domain of the function f intersects the range of the function b. This condition also means the following: the range of b contains some point of the relative interior of the domain of the function f. Note that this condition is always satisfied if f is a real value function. That means f of x is a real number for all x in Rn. Then we have the following subdifferential chain rule. The subdifferential of the composition of f and b at x bar is equal to A transpose of the subdifferential of f at y bar. Over here, as we see earlier, y bar is equal to b of x bar. Okay. Now, in the previous proposition, we already proved that this inclusion is always satisfied. And note that this inclusion doesn't require this assumption. Now, under this assumption, we will show that we actually have this inclusion and therefore obtain this nice equality. Okay, so let me go ahead and give the detailed proof of the main theorem of the section. Now, fix any u in the subdifferential of the composition of f and b at x bar. Our goal is to show that u belongs to the set on the right hand side. Now, by the definition, the inner product of u and x minus x bar is always less than or equal to the composition of f and b of x minus the composition of f and b of x bar, which is the same as f of bx minus f of bx bar, and this is true for all x in Rn. Okay, in order to show that u belongs to the right hand side of the formula, we're going to use a geometric approach. In order to accomplish that, we define the following sets. Omega 1 is the Cartesian product of the graph of B and R, and omega 2 is the Cartesian product of Rn and the AP graph of F. Note that both of these sets belong to the Cartesian product Rn times Rp times R. Okay, let me continue the proof with several steps. In the first step, I'm going to show that u0 minus 1 belongs to the normal cone to the intersection of omega 1 and omega 2 at x bar, y bar, z bar. Over here, y bar is equal to b of x bar and z bar is equal to f of y bar. We fix any element x, y, lambda in the intersection of omega 1 and omega 2. Then we have the following. Because omega 1 is the Cartesian product of the graph of B and R, so we have that this element xy belongs to the graph of B. So y is equal to b of x. At the same time, x, y, lambda belongs to omega 2. So the order pair y lambda belongs to the AP graph of f. So lambda is greater than or equal to f of y. Thus, lambda is greater than or equal to f of y, and f of y is equal to f of b of x. Now we have the inner product of u0 minus 1 and x, y, lambda minus x bar, y bar, and z bar is equal to the inner product of u and x minus x bar plus the inner product of 0 and y minus y bar plus minus 1 times lambda minus g bar. Note that the inner product in R is just the usual product. So we have the following. This is equal to the inner product of u and x minus x bar minus lambda minus, because of the definition of g bar here, we have the following. G bar is f of y bar and it is f of b of x bar. So this is lambda minus f of b of x bar. Now we're gonna use the fact that lambda is greater than or equal to f of b of x bar of x to have the following. This is less than or equal to the inner product of u and x minus x bar minus, we replace lambda by f of b of x minus f of b of x bar. Okay. Now at the beginning we let u be an element in the subdifferential of the composition of f and b at x bar. So by the definition, the inner product of u and x minus x bar is less than or equal to f of b of x minus f of b of x bar for all x in Rn. So this is always less than or equal to 0. Okay. Now by the definition of the normal cone, we have that this inner product is less than or equal to 0 for all x, y lambda in the intersection of omega 1 and omega 2. Therefore, by the definition of the normal cone to convex sets, we have that u0 minus 1 belongs to this normal cone. Now let me continue the proof by applying the normal cone intersection rule. By the assumption made, the intersection of the relative interior of omega 1 and the relative interior of omega 2 is non-empty. At this point, we're gonna accept this to continue the proof. I'm gonna come back to this later. So by the normal cone intersection rule, we have the following. Zero u minus 1, which is in the normal cone to the intersection of omega 1 and omega 2 at x bar, y bar, z bar. And this normal cone is equal to the sum of the normal cone to the first set at this point and the normal cone to the second set at this point. Okay, so we have the following. Then u0 minus 1 is equal to the sum of two elements. The first element is u1, v1, w1 plus u2, v2, w2, where this element belongs to the first normal cone. And this element belongs to the second normal cone. Okay. Now we're going to use the structure of omega 1 and omega 2 in order to continue the proof. Note that because omega 1 is the Cartesian product of the graph of B and R, the element W1 here has to be 0. Okay, and because omega 2 is the Cartesian product of Rn and the epic graph of F, so the first element here, U2, is equal to 0. So we have the following. This is equal to U1, V1, 0 plus 0, V2, and here is W2. Okay, so now using this equation, we have the following. U is equal to U1. And also W2 is equal to minus 1. And here we also have that V1 plus V2 is equal to 0. So then we can write this sum as follows. U minus V2 0 plus 0 V2 minus 1, where we have the following. U minus V2 belongs to the normal cone to the graph of B at x bar, y bar. And over here, V2 minus 1 belongs to the normal cone to the epic graph of f at y bar, z bar. Now, let us apply the lemma presented earlier to have the following. Because U minus V2 belongs to the normal cone to the graph of B at x bar, y bar, we have the following. U is equal to the transpose of A times V2. And also, V2 minus 1 belongs to the normal cone to the epic graph of f at y bar, z bar. Over here, z bar is equal to f of y bar. So, V2 belongs to the subdifferential of f at y bar. Now, from these relations, we have that U belongs to the transpose of A of the subdifferential of f at y bar. Okay, so because whenever we take any U in the subdifferential of the composition of f and b at x bar, we see that U belongs to this set. Okay, therefore we have completed the inclusion of the theorem. This composition is a subset of this set. As promised earlier, I'm going to show that the intersection of the relative interior of omega 1 and the relative interior of omega 2 is non-empty under the assumption made. I'm going to show this by using the structures of omega 1 and omega 2. We have the following. The relative interior of omega 1 is equal to omega 1 and is equal to graph of B times R. Note that this is true because B is an R-phi mapping, so the graph of B is always an R-phi set. And so the Cartesian product of the graph of B and R is also an R-phi set. For an R-phi set, we can easily verify the following. If A is R-phi, then the R-phi hall of A is equal to A, and so the relative interior of A is also equal to A. Okay? Now, because omega 2 is the Cartesian product of Rn and the epic graph of F, using the very important theorem that involves the relative interior of the epic graph of F presented before, we have the following. The relative interior of omega 2 is equal to the relative interior of Rn times the relative interior of epigraph of F. So this is the set of all x, y, lambda, where x is in Rn. Over here, the order pair y lambda belongs to the relative interior of the epigraph of F. So y belongs to the relative interior of the domain of the function f. And also, lambda is strictly greater than f of y. Okay? Now, because this intersection is non-empty, we can pick an element in this intersection. Pick y bar in the intersection. So y bar is in B of Rn, which is the range of B, and y bar belongs to the relative interior of the domain of F. So now y bar is in B of Rn. We can pick x bar in Rn so that y bar is equal to B of x bar. Over here, this is y bar. I'm sorry. Okay. Now, then we define the following element: x bar, y bar, and over here, f of y bar plus a positive number, for example, 1. Then we have the following: this is lambda, this is x bar, and this is y bar. So then this element, x bar, y bar, lambda, belongs to the relative interior of omega 1 because this element, x bar, y bar, belongs to the graph of B. At the same time, looking at the structure of the relative interior of omega 2, we see the following: x bar is an element of Rn, y bar belongs to the relative interior of the domain of F, and lambda here is strictly greater than f of y bar. Therefore, this element also belongs to the relative interior of omega 2. So, in conclusion, we have that this is in the intersection of the relative interior of omega 1 and the relative interior of omega 2. Okay, so we have completed the proof that this intersection is non-empty, and the proof is now complete.